All right, hello everyone. Welcome to lesson 18 of Calculus 1. So up to this point, we've been focusing on how to take derivatives of various functions. And in the last lesson, we learned how to take derivatives even for implicit equations where y is mixed in with the x. But now what we're going to get into is we're going to get into the applications of differentiation. And one thing that I really want to stress and remind you guys of is this word here, rates. So whenever we see something like a rate of change, anytime you see this phrase, then you can very likely express this as a derivative in some way. Whenever we see rate of change, if anything's ever changing with respect to time or distance or any other variable, we can usually write that down as a derivative. Now, what we're going to do today is we're going to look at various scenarios where things are changing, and we want to figure out how fast other things are changing, and we're not provided with that information. Now, all of these problems are going to seem very different from each other. And in fact, if you go over the homework and you even look at assignments on past exams and everything, all of these problems seem very different from one another. There's a different scenario in every problem. But don't let that intimidate you. One thing that all of these scenarios have in common is they're going to follow the same steps every time. So anytime we see one of these, they're called related rates problems, we're going to follow the same steps every time. The first step is typically to draw a picture. Drawing a picture can help you visualize the situation, and it'll help you in the steps that come down here. They'll also let you know if your answer actually makes sense, because then you get a kind of a physical scenario in mind. So I'd always recommend drawing a picture. Then I would fill in your picture, or at least write down the information that you're given, so the knowns, and then the information you wish to find out, or the unknown. So I'd write all of that down, and then especially focus on this, especially focus on what your goal is, what you need to find here. All right, after we've established all of our information in the scenario, then we want to make an equation. We want to make an equation that relates the knowns and the unknowns together. So hopefully we use our known information to help us get the unknown information. So we're going to make an equation, and sometimes this involves simplifying the equation as well. So sometimes we get an equation with too many variables in it, so we may need to use some information about the problem in order to eliminate some of those variables, or at least make things simpler before we move on to the next step. The next step here is to differentiate or take a derivative. And typically these derivatives will be with respect to time. Now there'll be some exceptions, but usually they're going to be with respect to time. So we do d dt of both sides. And often this will have us do implicit differentiation. So maybe we have, like, say, an h in there. We need to remember to multiply by dh dt when we're done with that derivative. Then once we get the derivative, then we plug in our information from up here and we solve for whatever we want. Now, this is very important. So there's a reason why this plugging in is included in the last step. If we plug in our specific numbers that were given back here, that will turn a lot of our equation into a constant. And as we know, if we take the derivative of a constant, we'll get 0. But that's not going to tell us anything about the variable that we want to solve for. So it's important that you don't plug in your numerical information, or at least most of your numerical information, until after you do the derivative, because then you don't have to worry about that part of the equation disappearing when it becomes a constant. So be sure to plug in your numbers after you do the derivative. All right, and then these are the same 5 basic steps for every single one of these related rate problems. Now, at first they'll seem kind of intimidating because they're going to be different every time, and we need to think critically about what's going on every time. But as we practice more and more of them, you're going to see that all of them will essentially boil down to these 5 steps in some way. So for the rest of the video, I'm just going to go over different examples, and I'm going to go through these steps for each one of these. So my first example here, suppose we have a cylindrical tank of radius 10 and that is filled to a height of 20 with water. Okay. Water is coming into the tank at a rate of 1 unit per minute. I suppose we could apply units to these. If we want to make it a little more realistic. We could say maybe 10 meters, 20 meters. And then since we have volume coming in, we could say this will be meters cubed. Right? So use meters if you like. We're not going to be huge sticklers about units here, so don't worry too much about that. I'll have your science teacher help you with that. All right, so this is all set up here. What we want to do is we want to find the speed at which the water level is increasing. We want to do this when it's filled to a height of 20 meters in our, this is probably a pretty large tank of water here. Okay, so let's go ahead and draw the picture. So that's our first step here. Let's go ahead and draw our cylinder. All right, and we know our cylinder is going to have a radius of 10. So this is step 2 here. We're going to write down what we know. So 10 will be our R. And then let's imagine that we have our water, and that's going to be filled up to a height of H, which will be 20 right here. We can also imagine that we have water pouring into the tank at 1 meter cubed per minute. Now, what sort of variable should we write down for this? Well, the volume of the water in here is increasing. So we see that word increasing along with volume. So this is talking about a rate of change of volume. So how do I express this? I'm going to write this as d capital V dt, and that's equal to 1. So this is the rate at which the water is pouring into the tank. All right, now what are we supposed to figure out here? Well, we want to know the speed at which the water level is increasing. So that's asking us about dH dt here. So we want to figure out the rate of change of h with respect to time. All right, so we finished step 2 here. We wrote down what we know and then what we don't know and what we want to know. Our next step is to make an equation relating all of this information together. So we have a volume quantity, a radius, and a height. So this makes me think we should write down the volume of a cylinder. So the volume of our cylinder is going to be pi r squared h. And the way to know that is it's the area of a circle, and then we just drag it along a distance of h. You know, v is pi squared h. So here's the equation we're going to use here. And then finally, what we're going to do is we're going to do the derivative of this. So I'm going to differentiate this with respect to t. All right, well, on the left side, we're going to have dv dt. On the right side, let's see what we get here. So we have pi, and then we have 2 variables here, r squared and h. So we should have to do the product rule here. Now, I'm going to do it for this problem, but in the future, I'm going to show you a quicker way of doing this, but I'm just going to do the product rule here for practice. So I'm going to take the derivative of r squared, which will be 2r, with the pi there. But since I did a derivative with r, I need to have a dr dt here. And then I leave the h alone. Next, I'm going to leave the r squared alone and do the derivative of h, which is the h dt. All right, so we did the derivative, and then now we just need to solve for what we want, which is this dH dt right here. Now, the problem is that we know what dV dt is, we know what H is, we know what R is, but they never said anything about dr dt. But this is where we need to think critically here. So if the water is pouring in here, and we know how water fills up a container, it kind of spreads out to do so, and it's moving upwards here, the radius of our water isn't changing at all. The only thing that's changing is our height. So if something is not changing, then its derivative has got to be equal to 0. So the radius of this container isn't changing at all. So dr dt will be 0, meaning that we don't have that term at all. So we're really just going to focus on pi r squared dH dt. All right, now that we've done the derivative, we can safely plug in all of our numbers. Because if we just plugged in numbers here and done the derivative, we would have at least gotten this being 0, and that's definitely not true. So let's see, dV dt is 1. All right, and then we have pi. Now r is 10, so r squared will be 100. And then we have the dH dt, which is what we're solving for. And then I'm going to divide by this constant, giving me my solution here. dH dt is 1 over 100 pi if I divide by that constant. And if you'd like to have units, you could do meters. Yeah, we're using meters here, meters per minute right here. So there we go. There is our answer for this. Now, one thing you may have noticed is that we actually didn't use all of the information here. Notice that we didn't use this h equals 20. What that means is that the rate of change of height doesn't depend on how high you actually are. So our height is changing the same as if the height were 10 or maybe even 0 as it is when we're at 20. So the height didn't actually matter for this. And sometimes with these problems, you may actually have superfluous information that doesn't actually help you. But it's still good to keep record of it just in case it may help. But anyways, we found what we were looking for. The rate of change of our height is pretty slow. It's 1 over 100 pi meters per minute. All right, so that's one example. Let's move on to another example here. Okay, so suppose a plane is flying overhead and it's 2 miles above the observer. So we're some person and we're watching this plane and it's flying pretty high up. It's flying 2 miles above us here. All right. So this problem is going to be a little bit strange. This problem is actually going to have an angle in it. If the angle between a vertical line and the observer's line of sight is theta equals pi over 4, and the angle is increasing at a rate of 75 radians per hour. Remember, radian is a unit for angle. How fast is the plane traveling? So if we know how fast we're tilting our head downwards to watch this, and if we know we've tilted our head downwards a total of pi over 4 radians here, then we need to know how fast this plane is going to be traveling here. All right. So let's go ahead and draw a picture, especially for this problem. There's an angle involved, so it's definitely helpful to draw a picture. So here's our little person here, and this person is watching the plane, which I'll say is going to be that. So there's a little plane going this way. And there's our line of sight here. There's our vertical, so this must be the angle they were referring to here. And then we can assume this is a right angle if the plane's flying horizontally. All right, now we know that this distance is 2 miles, and this distance isn't changing. This is how high the plane is And it doesn't say anything about the plane changing height at all. What is happening is as the plane moves to the right here, our angle is going to keep getting bigger and bigger, and our angle is increasing this way. So it's kind of coming down this way here. So what we need to know, what we're trying to figure out, let's say the distance from the observer's horizontal position to the plane's horizontal position is called x. We're calling this x right here. Then what we want to know for this problem is how fast the plane is traveling up here. We want to know what dx dt is. And we know that theta is pi over 4. And they also tell us the rate of change of our angle is 75 radians per hour. All right, so this is our setup for the problem here. And it's very important to read it carefully so you know how to set it up, especially when angles are involved here. All right, next, now that we've drawn the picture, we've written down our information, now we need to write an equation that's relating everything going on here. Now, what do we have going on here? Well, we have a theta, so we have this angle right here, and then we have two sides of a right triangle. So having an angle and then two sides of a right triangle, that makes me think of trig functions. That's definitely a function that will relate all of these together. So if my theta is here, x is my opposite side, 2 is my adjacent side, so that means I should probably use tangent. So tangent of theta will be x over 2. So this is going to be our equation here. Now you might be like, okay, well, Dr. Manley, you said earlier that we shouldn't plug in specific numbers until we've done the derivative. But there are exceptions to this. Notice that I didn't plug in pi over 4 for my theta, but I did plug in 2 for this distance here. The numbers you can plug in right away. So let me make a point of this. The numbers you can plug in immediately are the values that do not change throughout the problem. So if we imagine the physical scenario for this problem, this plane is kind of flying overhead like this. It's not going up or down, it's not descending or ascending. So this 2 is going to stay the same. But as the plane moves, this x is going to change, and this angle, we have to change the way we're looking at the plane in order to keep up with it. So we can't plug in numbers right away for theta and x, but we can plug in this constant value of 2. So anything that's going to remain constant in the context of the problem, you can plug in the number right away. Okay, anyways, we have our equation here. Now let's go ahead and do our derivative. So the derivative of tangent, we're doing d dt here. The derivative of tangent is secant squared, but then we need to multiply by the derivative of theta with respect to t. That's d theta dt. All right, over here, we need to do the derivative of x with respect to t, so that's dx dt. And then the 1/2 or over 2 is just a constant. All right, so now we're in a good spot. So all we need to do is just multiply by 2. So we have 2 secant squared of theta, d theta dt is dx dt. And we know what d theta dt is. We know what theta is, so we should be able to get what we want, which is dx dt. All right, so we have 2 secant squared of pi over 4 times 75. All right, now it is okay to plug this in since we have finished our derivative. So secant of pi over 4, we could compute that by doing 1 over cosine of pi over 4. Secant of pi over 4 is root 2. So if we square that, we get 2. This is all a 2. We have 2 times 2 is 4, and then 4 times 75 is 300. So I guess our units of distance were miles, and our units of time, I think they said 75 radians per hour here. So this is going to be 300 miles per hour. That's going to be how fast our plane is moving. So hopefully we learned from this one that it is okay to plug in numbers that don't change in the context of the problem, but it's not okay to plug in numbers that do change in the context of the problem. We need to use our imagination and imagine that this picture is kind of in motion here, and the things that don't change, we can plug in the number for. Also, it's interesting to note that we didn't need to know what x is here. So at the end of these problems, there may be quantities in which you don't know, but that's okay so long as you get the thing that you're trying to get here. So it's okay that we don't know what x is at the end of the day, even though we could figure it out by using this equation right here and plugging in pi over 4. All right, let's move on to another example. Okay, so in this example, 2 trains leave the same station. So this is like the most common word problem in math involving trains here. 2 trains leave from a station, one going north at 30 miles per hour, and one going east at 40 miles per hour. The north train leaves 1 hour before the east train. All right, so that might be important information here. One final piece of info, or one thing we're actually looking for here. What is the rate of change of the distance between these trains 2 hours after the north train leaves? All right, so we're trying to figure out how quickly these trains are moving apart from one another. All right, so let's draw our picture here. Let's imagine that this point is our train station, right? And the north train has moved this way. Now, the north train has been able to go for 2 hours. So if it goes for 2 hours at 30 miles per hour, I'm going to call this distance y for vertical, and we know it's going to be 60. All right, and then we have our east train that's moving this way. We'll call the horizontal distance x, and it only gets 1 hour to move because it leaves 1 hour after the north train does. So this will only be 40 right here. So we can imagine this is our east train, this is our north train, and then the distance between them is going to be this right here. I guess maybe we can call this s. S is a common variable for distance here. Actually, my s's look like 5. Why don't I call this, I'll call it L. There we go. Okay, so what we want to know is we want to know dl dt. So we want to know how fast the distance between these trains is changing if this train's moving this way and this train is moving this way right here. So we want to know what dl dt is. We don't need to know what L is, or at least it seems like they're not asking for that. We just need to know what dl dt is. All right, so it says north and east are perpendicular directions. This figure ends up being a right triangle. So since it is a right triangle, we have a relationship between x, y, and L here. Now, in the previous problem, I immediately plugged in 2, which was the value of one of the lengths. But for this one, I can't plug in any of these values because if we imagine this as a little movie in our heads, the train is moving this way and this train's moving this way. So these distances are constantly changing, as well as this one, of course. So we can't plug in any specific numbers right away. All right, but we need to make an equation relating x, y, and L, because these seem to be the 3 players here. Now, if we want to relate 3 sides of a right triangle together, we don't need to use an angle or a trig function. We should use the Pythagorean theorem. So we're going to use the fact that x squared plus y squared is going to be L squared here. All right, so with that in mind, I'm interested in knowing what dl dt is. So I need to do the t derivative of this equation. So this is step 4. I'm going to do my derivative now. All right, I do the derivative of x squared, which is 2x. But then since my derivative is for another variable, x may well depend on the variable. And it does. It's going to be how fast the stream goes. We have the same scenario for y. And then we have the same scenario for L. All right. So now what we need to do is we need to solve for dl dt right here. So one thing that can happen is that all of these 2's can cancel. And then it seems like the only thing that's also on the side with dl dt is L itself. So I'm just going to divide by L here. And then I have x, and I'm going to call this x prime, plus y prime, divided by L is dl dt, or L prime. All right, so if I know what all of these quantities are, then I can end up computing L prime. So it does actually matter what L is going to be in this case. So we do need to figure out L. So sometimes we need to figure out some stuff on the side before we can get what we're mostly after. Okay, well, how do we figure out L? Well, we can use the Pythagorean theorem with these numbers here. So we know that 40 squared plus 60 squared has got to be L squared. So this is 1600 plus 3600 is L squared. So the square root of 5200 is L. And we're going to put the positive, of course, because L is a distance. And we could simplify this. This will simplify to 10 root 52. I also think we can write this as 20 root 13. Because 52 is 4 times 13, square root of 4 is 2. Yeah, that's another way of writing it. So L is 20 root 13. All right, now we can go ahead and plug in everything because we know all of the rest of the information. We know that x is 40. We know that x prime, that's how fast we're moving in the x direction, or how fast the east train is moving. And the east train is going 40 miles per hour. So that will be a 40. Then we have our y value, how far the north train is gone, which is 60. And then we have y prime, how fast the north train is going. So that's going to be 30. And then finally, we divide by 20, 13. This will be L prime, what we want to know. Okay, so let's see here. I could definitely simplify this. The 20 could cancel, and this will become a 2. This will become a 3. So I have 80 plus 90 is 170 over the square root of 13. So this kind of bizarre number right here is going to be L prime. That's how we're going to be able to find out the rate of change of distance between these two trains right here. All right, so that's another example here. And in this case, we did need to find out what L was, whereas in the last problem, we didn't need to know what X is. So it totally depends on the problem. But notice that for all of these problems, the procedure has been very similar every single time. Draw a picture, write down what you know, write an equation, do a derivative, and then solve for what you want. They're all going to be roughly similar to this. All right, let's do 2 more. Now, I think the final 2 types of problems, these ones are a little bit more challenging. Okay, so suppose someone is pushing a swing of length, let's say 10 feet. And the swing is turning at a rate of pi over 4 radians per second right here. How fast is the swing moving? And this is the key component here. Horizontally, so we don't care about its vertical movement at all. We want to know horizontal movement after 1 second. Okay, so let's draw a picture. Now, a picture is going to be especially helpful for this one. Okay, so here is the swing when it's hanging perfectly downwards. It would be L equals 10. And then, so if we push it for 1 second, it's going to rotate at this speed for 1 second. So it rotates from being perfectly down like this. I guess I probably should have said that in the problem. Blank 10 that begins vertically. A bit more specific there. Anyway, so we start vertically and then we rotate at this speed for 1 second. So if we rotate pi over 4 radians per second for 1 second, we just go pi over 4 radians. So then after that, our swing is going to be like this. Now, it may be tempting to just continue drawing this and then make a triangle out of this. But one thing to remember is that the swing is always a length of 10 feet. It's not like rope is magically appearing and making this longer as we go along. So this length is still going to be 10 feet right here. So rather than a triangle, this is actually going to be a wedge of a circle right here. And then this is theta. Now, what we want to know here, so if the horizontal distance is x, we want to know dx dt. We want to know how quickly this is moving horizontally to the right here. Okay, now let's take a look at what we have here. So we know that our length of our swing is always going to be 10 feet. So that's a number we can actually just use the number for right away. We don't need to plug in the variable L for this. So that's not changing in the problem. What is changing is this quantity right here. We know that this is going to be, this is going to be changing. As the swing moves, our horizontal distance will be increasing. We can't plug in a specific number for x right away. They didn't even give us one. All right, and also we can't plug in anything specific for theta, even though at this current moment, theta is pi. So we need to keep theta as a variable as well, but L does not have to be a variable. All right, now we need to set up an equation. Now this is gonna be a little bit more difficult than usual here. Let's see what we know in this scenario. Well, we know what theta is, so we should probably include theta. We're interested in this x, and in particular dx dt, so we should include that as well. And then we also know about the length of the swing right here. So knowing two sides, now this is a triangle, so this dotted line x, this does form a right triangle. So we could use the fact that we have two sides of a right triangle and an angle to help us deal with this. So what I'm seeing here, I have the opposite side over the hypotenuse. It seems like x over L, or 10, is going to be sine of theta. I can move the 10 up here to get rid of the fraction. X is going to be 10 sine of theta. And this kind of makes sense if you plug in a few sample theta values. If I plug in theta equals 0 when this is hanging vertically, we'll have sine of 0, which is 0, and it makes sense that x is 0 there because we haven't moved horizontally. This does at least kind of pass muster, at least on face value. All right, so I have my equation. Now I'm going to do my derivative. So the derivative of x will be dx dt. Then I have the derivative of a constant times sine. Well, that will just be the constant times cosine. But then I must multiply by d theta dt. All right, now we actually know everything that we have here. So we know what theta is, it's pi over 4, and then d theta dt is also pi over 4. Now we can just plug in our numbers. 10 cosine of pi over 4 times pi over 4. Let's see, cosine of pi over 4 is root 2 over 2. So this will give us 5 root 2 times pi, and then we could divide by 4. Right there. All right, so there we go. So there is our dx dt. So this is how fast the swing is moving horizontally after it's been rotating or swinging for 1 second. This is how fast we're moving out horizontally. This might be important, for example, if you plan to jump off the swing, this is going to be your initial forward velocity. So that might be something you need to take into account, say if you want to get far enough to maybe land in a sand pit over here or something like that. Okay, I want to go over one final relay rates problem, and this one gives a lot of people trouble, so pay special attention to this one. So suppose someone who is 6 feet tall walks towards a street lamp at night that is 16 feet tall at a rate of 5 feet per second. How fast does the tip of the person's shadow move? Okay, so that's what we want to know for this one. All right, now this one's especially important to draw a picture here. So let's make this big line here. We'll say this is 16 feet. This will be our lamp post right here. And then we have our person here. This person is 6 feet tall. And then the way this works is the light shines on them and it creates a shadow right here. This is the person's shadow. So we want to know how fast this is moving. So what I'm going to do is I'm going to make up two quantities here. So the distance from the person to the lamppost will be x, and then the distance from the lamppost to the shadow will be L right here. And what we want to know is dl dt. Now, what's going to happen here is, this part is going to be L right here. So the length of this person's shadow is going to be L. All right, now we need an equation relating x and L, and then also using this 6 and 16 feet right here, and also the fact that they're going here 5 feet per second. All right, so what we're going to do here, you may not have seen this, at least in a while, we're going to use something called similar triangles to help us out. So notice that we have two triangles in this scenario. We have this big triangle right here, and then we have this smaller triangle that's sort of wedged in to our bigger triangle. Now, when we have this happening, when we have two triangles kind of sharing an angle like this, and one is contained in the other, these are called similar triangles. And one fact about similar triangles is that the ratios of their sides are the same. So for example, this vertical side, 16, divided by my long side here, x plus L, is going to be the same as 6, my vertical side here, divided by just L. And I didn't have to write this way. In fact, I think I'm actually going to write it the other way. I'm going to have x plus L over 16 is L over 6 right here. And this comes from similar triangles. So the ratio of the matching sides right here will be the same for these two triangles. And this will give us a nice relationship between x, L, and our given quantity. Now, why did I write down specific numbers for these? Well, as the person's moving towards the lamppost, the height of the lamppost isn't changing, and presuming they're not growing fast enough to have a change in their height. So these are going to be constant for the sake of the problem. That's why I plugged in specific numbers. All right. Next, I'm going to multiply by a common denominator here. I'm going to multiply both sides by 48. This will kind of help with the fractions here. So this is going to turn into 3x plus 3L. And then we have 48 over 6 is going to be 8. And then we could subtract 3L. 3x is 5L. And then x is going to be 5L over 3. All right, now why did I do all of this? Now when I do my derivative, then this will be very easy. I have dx dt here, and I have 5/3 dl dt. All right, so then that means that if I want to know what dl dt is, I just move this fraction over here. So I have that 3/5 dx dt is dl dt. And since my dx dt was 5, that means my dl dt will end up being 3 right here. This is what I'm going for here. My dl dt will end up being 3 for this problem. All right, so that's enough examples. Now, I highly recommend, among all the topics, this one definitely needs a lot of practice. You can get comfortable dealing with a different scenario every single time. But again, I want to assure you, the process for doing these every single time is going to be essentially the same here. All right, that's it for today's lesson, and we'll see some more applications in future lessons. So I will see you guys then.